This presentation is about design for manufacture and assembly, how we use our CAD tools day in and day out in terms of leveraging on the capabilities of three-dimensional CAD, specifically as addressed by quality requirements, which starts with manufacturing of the individual parts and assembling of the same. So design for manufacture and assembly has always been a challenging proposition when it comes to new product development or cost savings on existing products. What is design for manufacture? Design for manufacture actually involves the simultaneous consideration of design goals and manufacturing constraints in order to identify and address or eliminate, which other words means alleviate, manufacturing problems while the product is being designed, thereby reducing the lead time and improving the product quality. DFM, as it is called in short form, includes an understanding of the technical capabilities and limitations of the manufacturing processes chosen by invoking a series of guidelines, principles and recommendations commonly termed as producibility guidelines to modify the component designs for subsequent manufacture. In other words, if we are at the design stage able to address the manufacturing constraints, the capability of manufacturing in our organization or at our supplier's place, then we have a higher probability of getting the parts out and assembling them right first time. Let us look at what are the end objectives for which we develop a design. At the end of the day, it has to meet the customer's requirements, which is put together in the form of a statement of requirement. The statement of requirement encompasses the quality objectives as perceived by the client. So if we take design for quality as the first initiative in our design process, the flowchart over here shows to you the efficacy of this process in terms of releasing drawings at the design stage while meeting the requirements of DFQ. So from DFQ, you have the assembly objectives and the performance objectives. The assembly objectives and the performance objectives. The assembly objectives leading to design for assembly, leading to design for assembly, followed by the datum reference frames that are used for the definition of the part, and then you perform the tolerance analysis for all the parts put together to look at their variance, and taking the cost of precision and the cost of poor quality into consideration, doing what is called as the tolerance optimization and getting inputs from your DFMEA in terms of the risk priority number, classifying them as critical, essential and desirable, and then coming up with the key characteristics which then get onto the GD&T drawing that we provide. The inputs come from design for assembly in this process and the DFM, which is nothing but the design for manufacture, where the input comes from the process capability in terms of the centrality of the process and the process spread, namely by the CP and CPK. Then comes the cost indicators in the design for cost, design for service, transportation, performance, and from the performance objectives you get your design for life, which get influenced on the drawing, which is necessarily for mass production, uses the GD&T concepts. Now, the DFQ process starts with the definition of the quality parameters that we take as measurable objectives as the quality inspectors would want to go by. Now, when you classify this into two, the assembly objectives is where the DFM and the DFA come into picture. That's what we are going to talk about in this presentation. Now, the DFM rules and objectives start with identification of the key characteristics, that is the tolerances and the surface finishes that we put on the drawings, identification of the factors influencing the manufacturers of the KCs, the key characteristics, estimation of the manufacturing costs, minimization of the component cost, establishment of the maximum tolerance for each key characteristic. Remember, we are looking at maximizing the tolerance Otherwise, we would be running at cross purposes with the cost objectives, and subsequently determine the process capability for each key characteristic early in the design process. Avoiding the tighter tolerances, as I said earlier, forms one of the primary objectives while we are enumerating the DFM rules and objectives. The design part for easy inspection is absolutely important. Minimization of the number of machine surfaces that go onto the part, reducing the costs and the controls. Minimizing the number of reorientations required during manufacture for better accuracy and cycle time. Using standard manufacturing processes wherever possible to keep the costs low. Use of generous fillets and radius on castings, moldings and machine parts in order to help the design for performance in addition to the design for flowability in terms of castings and moldings. Now, as we proceed further on the DFM rules and objectives, holes in machined parts, castings, molded parts or stamped parts should be spaced such that they can be made in one operation without tooling weaknesses. These are some of the objectives and the rules that we need to follow as guidelines, a checklist before we sign off on a drawing. Parts should be used with sufficient stiffness to withstand the clamping and the tooling forces in order to minimize the deflections that could influence the specified tolerances. Design preference should be given for general purpose tools than for special tools because those increase the cost. So the manufacturing process selection drivers start with the product quantity that need to be delivered, low volume production, medium volume production, high volume production or one of a kind production. The equipment cost that is needed to develop this, the tooling costs, the processing time, the labor intensity and the work pattern, the process supervision, maintenance, energy consumption, overhead costs, material availability, material to process compatibility, commonization of material between different parts also helps purchase get a buying power for materials in a whole lot, and the component form and dimensions. These are some of the indicators that come in for the manufacturing process selection that drive the DFM considerations. The manufacturing process drivers in addition to these are the tolerance requirements, the surface finish requirement as dictated by the fit, form and functional requirements, the bulk engineering and surface engineering requirements, the process to component variability, the wastages that accrue in a process, and the component recycling or the waste recycling. Specification of general tolerances is one of the things that we start with whether we use SolidWorks or any CAD system. Here you can see that the user can have the option of checking fine tolerances, medium tolerances, coarse tolerances or very coarse tolerances, and the tolerances would set itself up based on the templates. This is enabled in the tools options of the SolidWorks CAD capability. Next comes a flagship requirement. Every organization has many engineers working on a project. If a person is on leave of absence or is no longer with the company, the drawing standardization becomes a challenge when new people take over. The automatic dimensioning and tolerancing using DimXpert follows the ASME Y 14.41 2003 standard of the American Society of Mechanical Engineers in terms of the digital product definition. You can use the plus or minus tolerancing, or you can use the geometric dimensioning and tolerancing. If you look at the circled area, you would be able to see the different types of the options that are provided inside SolidWorks for you to develop a complete and correct representation of drawings, either using plus or minus or using geometric dimensioning and tolerancing. Needless to say, the design for assembly reflects itself in the choice of the datums that we put on the drawings, the primary being the first surface that touches in that part, secondary being the second surface or the combination of surfaces that could touch the part, when the part gets into the assembly, and the tertiary one. These three are required for orienting and positioning the part with respect to other components in the assembly. Now, you can see a part definition released using the three-dimensional annotations with DimXpert, which is live annotations, which are representative on the features themselves. And you can see the basic dimensioning, the feature control frame, and the associativity of the different levels of control, starting with the size tolerance, with the form tolerance, the orientation tolerance, and the location tolerances being provided, and automatically representing the same in a two-dimensional drawing, laying it out in a clear manner and sending it out. Most of the times that a design engineer spends is on the drawing, specifically in terms of the correctness and the completeness of the tolerance specifications on the drawing as required by the design for manufacturing requirements. When the process is automated using the DimXpert, it is one step closer to achieving the objectives of DFM and A as we go about releasing the drawings. Undercut verification is another one which could help before a tooling gets stopped or the tooling gets lined off in the verification on the process. This is very important, especially when we are signing off on the tool. And then the draft analysis for looking at the drafting, whether the draft required on the castings or the mold are adequate enough. You can check this as well. Additionally, if a component is symmetric, you can verify whether the design has really been exploiting symmetry and make sure that errors are not created in assuming symmetry and looking at the deviations of the parts one side versus the other in terms of the symmetric checks. A lot of times people forget to put the machining symbols, surface finish symbols, or the flatness or the surface form control symbols on the drawing as required by the machining operations. SolidWorks, with the help of a few macros, you will be able to represent the machine surfaces with different color coding according to the requirements of the organization so that these don't get missed out and are a part of the checklist for the DFM process before the drawing sign-off happens. If it is there on the three-dimensional model, the annotations can be forced to come onto the two-dimensional drawing. As the part evolves, the drawings get updated as well. Now, the clamping force and the deflection calculations are required, especially when we are doing machining. Let us say we need a flatness tolerance on a surface and it's an aluminum part. The flatness is, let us say we require 10 microns for some requirements in fit, form and function, let us say leakage. Now, if we do not provide enough support surfaces on the datums or the locating pads, or the stiffness of the component is inadequate with regard to the tooling forces that come during entry and egress of the tool, then we have deflections coming into the part as the machining operations take place, and once the clamping loads have been removed, the part loses its flatness. These can be studied using a simple single touch tool to look at the clamping force adequacy and their effects on the deflection on the part. A requirement for DFM as well, which typically gets missed out at the design stage, primarily because it is perceived as the requirement or the objectives of manufacturing and not as a part of the design per se. However, if the lack of stiffness is going to be there, manufacturing is not going to be able to achieve the stiffnesses that are required for the deflections to be contained and the flatness to be contained thereon. The checklist for DFM also includes the DFMXpress, where the depth to diameter ratio, the milling, the undercut requirements or the analysis, and a lot of different aspects of design for manufacture is automated so that the people can go through this checklist and see where the tolerances or the wandering of the tool could affect the tolerance maintainability, and you can check the DFM for the sheet metal components, for the turned components, for the milled components and so on. This is an automated process that every engineer can go through before signing off on a drawing. It is time well spent at this point, which helps us to save on costs and grief down the line. Material selection drives the cost. So at the design stage, if we look at the alternate materials, in terms of the stresses, in terms of the factor of safety, in terms of the displacements and things like that, we would be in a position to select the right materials which are required for the least cost at the design stage, because material selection influences the manufacturability as well. This is well built in terms of the design studies that come in SolidWorks. As we talked about earlier in the checklist, we were looking at the recyclability. Recyclability is a synonym with sustainability. So it starts with the raw material extraction process, the material processing, the part manufacturing, the assembly, the product use, and the end of life. This sustainability requirements can be checked on SolidWorks models either in the parts or in the assemblies, as is shown in the next picture, wherein the water utilization, the energy utilization, the material, the effect of the material and the recyclability of the earth, and the carbon footprint, which addresses the CSR responsibilities, the corporate social responsibility in the organization, because the government regulations and norms are coming forth. This is a part of the design for manufacture as well. So the sustainability can be checked. Now comes the most important thing. What is the cost for the different processing methods? As can be seen in this table, the different relative costing with cold forming versus machining, powder metallurgy, sintering versus machining, deep drawing versus spinning, sand casting versus closed die forging, cold extrusion versus machining. These are some of the examples that we can look at how the cost influencing factors can be chosen upfront for the manufacturability of the part. It is incumbent upon the design engineer to sit with manufacturing to understand the costs involved, and if we tabulate the processes and come up with the least cost designs from a manufacturability point of view, it's a win-win game. So the costing inside SolidWorks helps and enables customers to develop the costing at every stage of manufacturing in terms of a template-driven design for costing approach. You can take sheet metal components, you can take machined components, you can take a lot of different machining operations, and you can come up with the design for cost. So earlier in the design process, the machinability cost and the overall cost of the product can be evaluated by the design engineers and against the cost objectives of the organization, where this return on investment with regard to these kinds of 3D tools is assured. Specifically, cost is the driver that could make or break a product in an organization. So once this is done, the costing report is provided for the machined components and the alternatives, and the person would be able to understand what is the eventual cost of this product based on templates that are driven by supplier costs, material costs, or in-house costs, or a combination of these. As you can see in this report, for every single portion of that, the cost itemization comes in. So design for manufacturability, where cost is a driver, where the options are told to the manufacturing based on the different alternatives available, helps us to reduce the cost at the design stage itself. A problem solved at the design stage costs very little money as compared to the same problem being solved either during tooling up or during assembly or at the end customer's place. So the DFM and A process starts with the product design specification, coming up with the product design and looking at the part count analysis, the design of the component for ease of handling and insertion, and the assembly costing from an assembly point of view, the material selection, the process selection, the design for the process, and the component costing as a result of this. These two coming together are then put as input and gone through the process, and the design reviews are conducted, and the cyclical nature of this iterative process helps us to refine our designs for least cost in manufacturing and assembly. And then the finalized stage is provided for manufacturing sign-off. As you can see here in the next picture, the business analysis of the 4 sectors. The first segment dealing with the more robust design. The second segment dealing with the better marketing, and the third segment dealing with the profit and loss analysis, and the last segment dealing with the better manufacturing processes. As the tolerance increases, as the clearance increases, the performance necessarily comes down. As both of them reduce, the performance increases, but it leads to a robust design. But as can be seen from the manufacturing cost, the better manufacturing processes have to be put in place, which in the fourth quadrant, when extrapolated to the loss or the profit, you can see on the left hand side, you see the revenue and the cost, and you're able to see the drivers which are coming in. So at the end of the day, the tolerances that are specified on the drawing when making a business case of this kind helps us into having a successful product where the cost of ownership of the product for the end customer is as little as possible. Subsequently, the process selection flowchart can be seen over here. From the product design specifications, the PDS or the SOR or the statement of requirement, we obtain the relevant process selection inputs, the annualized production, the quantity, the material type, the thicknesses or the permanence of the part, and then using this as the design data, we select a candidate process from a lot of different ways. One of the popular methods is called as the priority information mapping and allocation. This PRIMA method is used popularly in the industry. It's based on a matrix, and the strategies of this are taken as inputs, and the list of candidates in the processes are further refined as shortlisted candidates based on each PRIMA characteristic consideration against the technical and the economic requirements. Subsequently, the business factors play a part, and then the selected process goes mainstream. The PRIMA matrix is shown over here in terms of quality as you go down from the top to the bottom, and from left to right it is the different materials and their alternatives. What you are seeing is the numeric indicators of the PRIMA entries into the different squares of the matrix, where each one of those numbers represent the different processes. These guidelines in the PRIMA matrix, when you put it together, you could even automate it inside SolidWorks by writing small macros and lookup tables, driven by Excel as well. So this gives you a brief bird's eye view of the design for manufacturing based on the selection of the material based on the processes in manufacturing. Now comes the assembly considerations. Business level considerations, product level considerations, and supplier level considerations are three different drivers that help us to understand the assembly constraints when we put together the design. The business level considerations are identification and availability of assembly technologies and expertise in-house, integration into the business practices and the strategy, the geographical location, and the future competitive issues such as investment in equipment. The product level considerations involve anticipated lead times, product life, investment, return time and scale, product families and variants, and product volumes as required. The supplier level considerations include the component quality, the process capability, and the gross defects that a particular line is capable of delivering, and the limitations thereof, and the timely supply of the brought in and the in-house manufactured costs. Mind you, these assembly considerations in terms of business level, product level, and supplier level are dynamic. So once you sign off, we need to keep revisiting this as a part of the continuous improvement process, so that as the life cycle of the process progress happens, from a cost consideration point of view, we would necessarily have to revisit this to keep the profit margins intact, if not better. The DFA considerations are, some of them are, you could use this as a checklist: availability of labor, operating costs, production quantity, the capital cost of assembly equipment, the production rate required, the number of components in the assembly, the number of product variants, handling characteristics in terms of safety, environmental hazards and supply logistics, complexity of components in assembly operations, size and weight of the components to be assembled. Now, here if you look at it, the number of product variants is in our hand. The design for assembly considerations, I will give you a simple example. If a component requires 6 fasteners, 6 M12 bolts or M8 bolts, let us say, if we are able to reduce it to 4 M10 bolts, then 2 less drilling needs to be done in 2 different components. If it's a flexed fastener with a tapping on one of the component, tapping operations are eliminated for 2 of them. Packing list contains 2 less components, and then you have your assembly time, the fastening time, and everything else comes down. So the number of components in the assembly, if components are integrated together, then we have integrated designs which help us to reduce costs. One of the flagship products at Ford, for example, it has been given in a case study, is that they reduce the number of components going into the front end of a car from over 100 to 18 components. In other words, their contemporaries, General Motors, used to have 103 components, while the number of components going into an assembly in Ford car used to be 18. So when the number of components come down, the dynamic interaction of the tolerances based on the position and the orientation of the components in the assembly comes down drastically, leading to less number of things that need to go wrong or that can go wrong in an assembly or in a part production process. So DFA considerations could make or break a company. The assembly system classification, again a PRIMA system, as you can see over there, it could be a manual system wherein the human operators are involved with a transfer system or a single station. It could be a programmable robotic flexible manufacturing flexible systems, or it could be a dedicated special purpose systems. Depending on the nature of the systems, the classification of the assembly and the decisions that need to be taken thereof are dictated. For precision, sometimes human operator bias needs to be eliminated, in which semi or full automation of the assembly is a prerequisite. For example, basis for the assembly selection are the number of product variants, the flexibility, and or the production rate, or the production quantity per annum or per month, or the capital cost of the assembly equipment that is required for this particular assembly of systems. The assembly system selection chart, as can be seen over here, could be manual, could be mechanized with or without mechanized assistance, could be flexible, it could be hard automation or semi-soft automation, or it could be dedicated hard automations as it is given over here. Now we can see from this, from the graph, we can choose the methodology that we need for the assembly systems that would drive up our costs or reduce our costs according to what design decides. If we look at the joining process selections, there are different methodologies that we can incorporate: functional, technical, spatial, miscellaneous, the economic considerations that go in a joining process selection. The PRIMA selection number that comes in, again, it is priority mapping, information mapping. You are looking at the welding processes, the brazing processes, the soldering processes, the adhesive bonding processes, the mechanical fastening techniques. Lot of different things are coming in together with the PRIMA numbers associated with it, leading to what is called as the PRIMA matrix for assembly. As you can see, depending on the materials, depending on the rate of production, the person has, at the design stage, the choice of selecting the different assembly processes. These can be put as a lookup table, either using Excel or using design tables inside SolidWorks, so that the design checklist gets further refined based on these processes, even for the uninitiated engineers and the trainees who are asked to develop product designs without prior knowledge of the manufacturing process. As you can see over here, the list extends for the different kinds of metallic and non-metallic components, including lead, composites, ceramics, plastics, and things like that. The PRIMA categories and the individual processes are given over here, which form a part of the matrix. So SolidWorks helps us, in addition to enabling us to include these as a part of the processes in design for manufacture and assembly. We are in a position to do the interference checking. in 3 dimensions, and it tells you exactly the level of integration. As you can see over there, even coincident mates can be treated as interference and it can be asked to show as highlighted, or the clearance checking that comes in as a part of the process as shown over here, or the assembly visualization as given by the different raw materials that are used for the process. This helps even manufacturing and purchase to streamline their processes based on materials, and the material flow gets streamlined inside the organization in terms of the process layout on the manufacturing shop floor. Now coming back to the DFM and the DFA, today technologies are available for us to incorporate the process capabilities. One of the things that manufacturing industries in India are extremely strong with are the statistical process control data that they collect. How can design leverage on that data for maximizing the product quality, for reduced cost, and for customer satisfaction in terms of quality objectives upfront? This is where leveraging on the CP/CPK of the processes or dictating minimum process capability as a part of the process helps us in understanding the prioritization of the design for manufacturing and assembly considerations when we are releasing the drawings. More said than ever before, with competitive manufacturing coming into picture, these kinds of tools and technologies as available with SolidWorks can even help a person who's putting the part tolerances on the drawing to understand the assembly process, the effect of the assembly process in terms of PPM with respect to the measurable objectives on qualitative parameters that quality inspects subsequently down the line. For shifted processes, for depleted processes, for best-in-class processes, based on the CP/CPK, the tolerances and their effects in the part and the assembly quality can be checked up front. In other words, the overall product development cycle time comes down because more emphasis is now put on the design. Translating an idea or a concept in design to a workable product in consistent quality is always a challenge in any organization. These kinds of tools and technologies help in leveraging these kinds of challenges and making sure that upfront, in order to achieve first time right, the checklist can be given to the designers so that they can automate this as a part of the process before releasing the drawings. The advantage of this is that, let us say we take the case of 100 parts which are being tested. 10 parts failed, the 90 parts passed the requirements. The same drawing was used for all the 100 parts, but 10 parts failed, 90 passed. It could be material, it could be manufacturing considerations, it could be the allocation of the tolerances or the criticality of the tolerances, or the design considerations in terms of repeatability in manufacturing being addressed at the design stage. Any which way we look at it, the burden or the challenge gets transferred from manufacturing and assembly to design, more so with the innovative technologies coming in, so that the overall product development cycle time and the time to market can be reduced as much as possible. This presentation gives you the emphasis on DFM and DFA as a prerequisite in design so that we can leverage on these tools and technologies to develop qualitatively better designs. One example is, let us say we look at the welding. The weld in a system leads to what is called as heat affected zones, leading to shrinkage and loss of tolerances after the components have been welded together. Can we study it? Yes, you can. With an integrated product design and process selection as a part of the product development process, we are enabling, these are all enabling technologies at the design stage to address the design for manufacturing and assembly requirements. So the benefits of DFM and A using SolidWorks, institutionalizing it at a part of the process helps you to get your products out first time right. Improve the profitability because you know exactly upfront the cost. If the cost as a driver is given to the design department and targets are provided to them, they can try and achieve those cost drivers to keep them under control so the overall profitability of the organization is not under threat. Reduced service calls subsequently down the line and a good customer experience is a byproduct of following the design for manufacture and assembly as a part of the design process. Enhanced quality, either as perceived by the customer or as delivered by our suppliers, is an assurance that comes in as a result of adhering to the design for manufacturing and assembly process. One of the most important things that we need to understand in this process is that the design cycle time gets extended. However, the overall product development cycle time gets shortened. Some of the companies have reported 20 to 25% reduction in the overall cost of their product as well as in terms of the development time, primarily as a result of adhering to the DFM and A process as a part of the design early in the design stage. A simple example is a starter motor that Denso produces in Japan. They have 6 different product parts coming into an assembly, got reduced from 20 different parts to 6 parts, each part having 3 variants. So when you take the combination, you get 729 combinations of the product variants. Necessarily you will have to come up with an automation process. So as a part of the design for manufacturing and assembly considerations, they have developed a fixtureless assembly. For example, one of the component itself becomes the fixture. These kinds of unique methodologies that we can adopt as a part of our process helps us to get how quickly we can get the product out into the market with the least number of iterations. This is absolutely important when it comes to looking at first time right, profitability and enhanced quality of our parts. Now we invite you to provide us with questions that you may have as a result of seeing this presentation, and we shall be glad to address the same. Kindly put your question on your chat screen so that we shall be glad to address the same. How does SolidWorks help us to arrive at tolerances? It's a very good question. Different manufacturing processes have different process tolerances that can be achieved. If you look at the lookup tables that are provided in guidances in DFM and A online repositories, you will be able to come up with the initial selection of tolerances. And then you can use SolidWorks with either its Tol Analyst, which comes inside SolidWorks Premium, to see the effect of tolerances in the build quality. Or you can use an add-on tool called as Segment, which works inside SolidWorks, to look at the effect of the tolerances, and then as we had seen on the DFQ process, to optimize those tolerances based on the production capability or the manufacturing capability, in addition to the cost of precision and the cost of poor quality, to come up with the tolerance optimization. This helps us to arrive at tolerances based on optimizers which are available inside. We develop special purpose machines. How will, for office system, furniture, manufacturing, how will SolidWorks help? Office system manufacture, there are two different kinds that we are looking at in terms of the overall cost of the product. One is the number of components coming together. The other one is the failure of the components because of use or abuse. Third one is the foolproof designs that we need to put together. The transportation costs and other things come in the furniture. In all these considerations, we would be in a position to arrive at the cost, the design for costs, and the stage-wise manufacturing process costs as a part of the capabilities inside SolidWorks to address the manufacturing sector. In addition to that, the DFMXpress can be helpful in looking at whether the depth to diameter ratio, the undercut and things like that can be resolved upfront in design. The number of components going into the assembly also can be reduced so that the assembly cycle time comes down. It could be that you are selling the product as a disassembled product so that the customer assembles it by himself. Or it could be a product which is assembled in the shop, in the factory, but it is disassembled and reassembled at the customer's place. A lot of different ways in which are designed for transportation. You have to put it into a packing container and you have to send it. The maximum number of furniture going into a container before it is shipped. A lot of different areas in which you can use this to come up with reduced costs. We develop special purpose machines. How would SolidWorks help us to develop SPMs faster? If we cannot assemble it inside SolidWorks, you cannot assemble it on the shop floor. You give the nominal dimensions, you give the tolerances, the effect of the tolerances on the assembly, and the variation of the same affecting the assembly process subsequently down the line, you can study that. One of the things about the special purpose machines is we use a lot of mechanisms. For example, timing mechanisms like Geneva Paul mechanism, CAM mechanism, actuating mechanism. So many different things that we use. The SolidWorks premium module includes the ability to check the animation of the assembly. And you have the SolidWorks simulation, which also is an add-on module with an integrated Adams solver, kinematic solver, which helps us to look at the forces, the actuating forces, the efficiency, the velocity ratio, the maximum mechanical advantage and things like that, that can be put together for developing, synthesizing the mechanisms for optimal costs. Does SolidWorks help in increasing productivity? If we are talking about design productivity, there are excellent automation tools that are available inside SolidWorks that people leverage on to release drawings automatically. The advantage of this is that the drawing, whether it comes from an X, Y or a Z engineer, is remaining the same and it is adhering to the company's policies and drawing practices. Second, a lot of times we see companies having limited number of resources in terms of engineers, primarily because good engineers are hard to find. So they want to automate the process so that irrespective of who works in the organization, the knowledge with regard to the design process gets embedded so that the productivity of the individual can be increased. Here also people are using it. An example is one of our customers got an operational excellence award specifically in terms of productivity for what is called as the skids, oil and gas skids, where the request for customer comes, they put the skid using automated processes inside SolidWorks, route the cables and wires and pipes, and then generate the bill of materials automatically, and then send the GA drawing to the customer. Another case is where the RFQ comes from a customer and it is for a battery manufacturing. The RFQ gets converted into assembly drawings and the part drawings with sheet metal and plastic components, and then gets signed off for the GA drawing to be approved by the customer, so that the overall RFQ time comes down. So if we are looking at productivity of the entire organization with the lead time coming down from an RFQ response time, yes, it is possible. If we are talking about the productivity as far as the individuals are concerned, yes, more number of parts can be designed correctly without iterations, without having errors creeping into the drawings, which helps us to avoid the productivity losses by rework. All these things are small checklists that can be built into the process so that a person can leverage on the tools and technologies available inside SolidWorks to improve their productivity. These kinds of tools need to be enslaved so that our overall contribution of time in the organization is more towards purposeful design than towards processes which can be automated. I hope I have answered your question. Next one. How can, you had mentioned about the clamping forces that are coming in, how can they be studied? Okay, we had a case where one of our customers was looking at a 5 micron tolerances on the surface of an aluminum casting, LH-RH castings coming together to seal the system because it is filled with oil. Leakage was one of the requirements. Now they were not able to achieve 5 microns flatness in spite of developing an SPM, a very robust SPM system, and they asked us to come and investigate. We dialed the system, we looked at it, and then we came back and we saw when the tool enters and the tool leaves the component, the maximum imbalance comes in, and the clamping forces also make the component bow in one way or the other. So after the component has been clamped, the tooling forces act upon an already deformed object and the machining starts, and after the machining was over, when you declamp it and you look at the flatness, it is all over the place. This was solved primarily by looking at the stiffness and the locating parts, the datum targets, by the way, the datum targets, which are helpful for us so that we can do it the first time and maintain the stiffnesses, because nobody gives stiffness as a tolerance, as a requirement for the manufacturing process. We put on the drawing what the flatness we require. How are we going to achieve it? We don't tell that to manufacturing how we need to do it. A simple finite element study would have helped us to do it. Any other questions? We would be glad to address the same. Anything else? No. How does SolidWorks help in data management and storage space when compared to other softwares? In storage space, the software itself optimizes the storage space that is required for storing these parts, however the size of the files. More than that, the configuration inside also helps us to reduce the part size, the disk space. But if you are looking at the data management, SolidWorks has data management toolkits available called as the Enterprise PDM, which helps us to automate the workflow process as well as the notification process, so that the revision control, the version control, as well as archiving of the data and things like that can be done instantaneously, and the progress in a collaborative environment can be done. So Enterprise PDM is a product from SolidWorks which works with SolidWorks, AutoCAD, Solid Edge, Inventor, Pro Engineer, so many different softwares with CAD and non-CAD files and entities, so that the entire process in an organization can be mapped and the data can be managed. This is one of the things that we have been successfully doing with quite a few customers. If you are interested, we shall be glad to get in touch with you to address your specific requirements. Are there any other questions? Well, thank you very much for your time spent this afternoon with regard to the design for manufacturing and assembly. We hope you enjoyed this presentation. We look forward to interact with you more in the future. Till then, thank you. Have a good day. Goodbye.